Today we're going to talk about section 7.5, which is about complex numbers as vectors. We've already talked about this a little bit. We're going to kind of get some specifics about vectors this time, though. It's much easier to deal with this if you have graph paper, so make sure you have some graph paper to deal with this. We talked about how if we have a complex number, we can write it as a vector, and we used this notation with the half arrow and the little pointy parentheses. And what this means is this complex number is 5 plus 3i. So 5 is the real part and 3 is the imaginary part. So if we have these, let's give 3 vectors here. We have 3 vectors, and in this case, these vectors represent complex numbers. If we want to add these vectors, there's a couple of ways that we can do this. Now, we can do it graphically. Now, like I said, this is much easier on graph paper, so you want to have some graph paper available. So we have u here. Now, we always said that we start at the origin and we go to this terminal point that is the coordinates of our real part and our imaginary part. So this is u. But when we want to add vectors together, what we do is we start with the first one and we take the tail of the second one and put it on the head of the first one. So from this point here, we're going to want to go to our v vector. So what this means is we're going to go to the right 3 more, and then we're going to go down 6. So we went 1, 2, 3 to the right, and 1, 2, 3, 4, 5, 6. And that gives us our terminal point for this v vector. Now, vectors are the same if you can move them all over the grid however you need to, and they're still the same length and they still have the same argument because they're still going in the same direction. So they still have the same magnitude and direction, but we have to move it if we're adding them. When you add vectors, you move this second one so that its tail is on the head of the first one. And then what you end up with is if you go from the tail of the first one to the head of the second one, you end up with this new vector, u plus v. Now, what point is this here? Well, this point is the point, let's use our proper parentheses here. This point here is 8, negative 3. Well, what that means is this new vector is 8, negative 3 because it started at the origin and it goes to 8, negative 3. Now, you can also do this analytically. You can take the individual vectors and add the real part and add the imaginary part to end up with the new vector. And you see that you get the same thing. You should, because it's the same problem. You can do it graphically and you can do it analytically, either way. Now, let's try another one. What if we have, instead of wanting to add these, well, yeah, let's just erase the whole thing. Instead of wanting to add these, what if we have the same vectors from before? We have v minus w. So what that is, we need to remember that subtraction is the same thing as adding the opposite. So what we're going to do is we're going to take our vectors. We've got v is 3, negative 6. So that's our first vector, so we just graph it normally. There's v. Now, w is negative 6, 8. So normally what we would do is go to the left 6 and up 8 if we were just adding w. But we're not. We're adding the opposite of w. So instead of going left 6, we're going to go right 6. And then from there, instead of going up 8, we're going to go down 8. And we end up over here. So we go from the tail of V, we put the tail of W, of opposite W, onto our V, and we end up with this opposite W vector, so that when we draw in our sum, we go from the origin, the tail of the first one, to the head of the second one, and this is our V minus W. So where are we down there? Well, down here we're at 9, negative 14. Now, could we do this analytically? Of course we could. We take V, which is 3, negative 6, and we add the opposite of W. So the opposite of W is where we change the signs of both of them. So that means we have 3 plus 6, negative 6, negative 8. Which gives us 9, negative 14. So we can do this graphically or analytically, either way. Just remember when you do it graphically that you need to line them all upright. So we have to put the tail of the second one on the head of the first one, and then we have our sum vector. Now what happens if we multiply these vectors by a constant? Let's say we have 2u. Well, 2u would just be 2 times our u vector. We're still using these same ones we set up at the beginning. So all you have to do is multiply 2 times the real part and 2 times the imaginary part, and you have this new vector, 2u. Now, could we do that graphically? Of course we could. We've got u here. So to have 2u, we just need to put another u on top of there. So we just go over 5 and up 3 again, and we get this new u, so that the whole thing together is 2u, which is our 10, 6. And what if we have 1/2 w? Well, again, it's the same thing. We have 1/2 times, or let's do negative 1/2. We have times negative 6, 8. So we end up, multiply it times the real part, multiply it times the imaginary part, and we have 3, negative 4. Now how could we get this? Well, if we have our w vector, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So here's our w vector. So what we want to do is take this vector and shrink it by half and flip it over 180 degrees. So we're flipping it straight this way and making it half the length. So half the length is at 3, negative 4, and we flipped it 180 degrees. That's what that negative sign does. And there's our w, our negative 1/2 w. So the negative flips it over, and the half changes how long it is. Now, what happens if we want to say 2u minus 1/2 w? Well, now we're taking this vector and putting them together. So we've got our 2u. So now we need our negative 1/2 w to be on the end. So we have to start here, and then we need to go left 3 and down 4. So we go 1, 2, 3, and we go down here. So we moved this one. See how they're parallel? They should be parallel. We just slid it right down that vector so that we could line it up properly. so that in the end we can get our sum vector. This one here is the 2u minus 1/2 w, because we took our 2u and then we put the minus 1/2 w on the end of it. So from the origin to that end is our new sum vector. So what does that mean? Well, our 2u is 10, 6, and our minus 1/2 w is our 3, negative 4. So we add the real parts and add the imaginary parts, and we end up, if we see here, this point right here ends up at 13,2. Count it off. You use straight edge and graph paper and you'll see that that's exactly where we ended up. So again, you can do it analytically, but you can also do it graphically, and you need to be able to do it both ways. Now, we talked about how we have a complex number, and we would call it a plus bi, but we could also use this vector notation, a comma b, with these funny parentheses. Well, there's another thing here that we need to deal with called unit vectors. Now, this is going to be a little bit complicated, or not complicated, but confusing maybe, because we use I here, except it's not the imaginary I. So we have our graph here, and remember, a unit something means that it's 1 unit long. So if we have a vector here that's 1 unit long, and it goes down only on the real axis, so this is a real unit vector, we call it I, but it's a vector, so you put your little vector notation on the top. And we also have, let's use a different color, one on the imaginary axis where we go up, and this one hits at 0, 1 because it's only going in the imaginary, and we call it j. Now these are vectors. They're the unit vectors. I is the real part and j is the imaginary part. So when you have a complex number, you can write it just as a complex number. You can write it in this kind of vector notation, or there's another kind of vector notation where we write it a times this unit vector I plus b times this unit vector j. Because what that's saying is we have a times 1, 0 plus b times 0, 1, which just gives us our a, b, which is what we had. But this tells us this is how far we're going in the real direction, this is how far we're going in the imaginary direction. So if we have, let's say, our u that we had used before is 5, 3, then for the other kind of vector notation, we would write it as 5 times the unit vector I plus 3 times the unit vector j, because we're taking 5 times this unit vector, so we go out here 5 times. So if our unit vector is here, this is I, this unit vector, we go do that 5 times. 1, 2, 3, 4, 5, and we end up out here. And plus, we're going 3 in this direction, so we have to go, we're adding them, so we go 1, 2, 3, so that in the end, u is this vector here, where we added a multiple of this unit vector plus a multiple of this unit vector. Most of it's just a notation thing. You need to make sure you know how to deal with this notation, and this notation, and realize that they are all the exact same thing. We're dealing with complex numbers and vectors. We're going to do some more with vectors. It's not necessarily complex numbers, but right now we're trying to just relate the two before we move on to using vectors without the complex number part. Because remember, we can represent complex numbers as vectors, but not all vectors are complex numbers. So make sure you know about these unit vectors. Make sure you understand this notation. Make sure you remember how to add them and multiply them and have read this section. We'll talk about this in class some more.